Graphs of logarithmic functions. If f of x equals 2 to the x, then the inverse function of f is given by f inverse of x equals log base 2 of x. So notice that the base of the exponential function is 2, and the inverse function, the base of the logarithmic function, is 2. We can sketch the graph of y equals f inverse by creating a table of values. So we've learned previously in the last section how to graph exponential functions. So I created a table of values just like we did in that video for y equals 2 to the x. Now remember, for inverse functions, you just switch the x and the y values. So we can figure out, once I have the points for the 2 to the x, I can figure out the points for log base 2 of x, since that's the inverse, by flipping the x and the y. So normally this first point is negative 3 1/8, and that turns to 1/8 negative 3. So let's graph that. Okay, and then I have negative 2 1/4, which becomes 1/4 negative 2. And then 1/2 negative 1. And then 1 0. 2 1. And 4 2. And this exponential function had for exponential function, they have horizontal asymptote at y equals 0. So again, if you switch the x and the y's, that means that this logarithmic function is going to have an asymptote at x equals 0, which ends up being a vertical asymptote. Okay, so this is what that graph looks like. So let's do it in blue. So again, if we have the points that are on y equals 2 to the x, and we know that log base 2 of x is the inverse function, all we have to do is switch the x and y values of the coordinate points, as well as the asymptote. So this is what the graph of log base 2 of x looks like. Now let's look at how to graph log base 3 of x, and hopefully we can find some similarities between log base 2 of x and log base 3 of x, and then we're going to generalize that. Okay, again, for creating the table of values for our inverse function, you switch the x and y values of the original function. So this becomes 1/27 negative 3, 1/9 negative 2, 1/3 negative 1, 1 0, 3 1, and 9 2. And again, this had an asymptote at y equals 0. So that means that this asymptote, since it's the inverse function, is going to be at x equals 0. Now notice this base a. So we have the points 1 0. That point was also on log base 2 of x. This point, which we could rewrite as the base a comma 1. Our base was 3, and the point 2 1 was actually on the last graph, log base 2 of x. And then looking here, here, you can see that the point 1 over a, so 1 over 3, negative 1 is on this graph. If you go to that last line, we also would have found that 1 over 2 for log base 2 of x, comma negative 1 is a point that was also on that graph. So let's generalize this for log base a of x. So now let's generalize this. For any real number x and constant a larger than 0, a cannot equal 1, we can see the following characteristics in the graph of f of x equals log base a of x. The domain. So remember that with an exponential function, we found that the domain was all real numbers and the range was from 0 to infinity. The logarithmic function is the inverse of an exponential function. So that means that the range of the exponential function, which was all values greater than 0, becomes the domain of the logarithmic function. And similarly, the domain of the exponential function, which was all real numbers, becomes the range of the logarithmic function. The asymptote. So there is an asymptote at x equals 0, so it's a vertical asymptote. Points. The 3 points that will always be on this basic graph of log base a of x are a1, 1, 0, and 1 over a, negative 1. And you can see that with the 2 examples that we did previously. The logarithmic function is increasing if your a is larger than 1. So the graph will look like this. And it's decreasing if your a values are between 0 and 1. So let's look at an example. Graph f of x equals log of x. Remember, this is the same thing as log base 10 of x. We know it's going to have this shape because it's increasing. The a is larger than 0 or 1, and it's going to contain these points. So that means our a value is 10, so it's going to contain the points 10, 1, 1, 0, and 1 over 10, negative 1. So I can use those points to graph this. So 10, 1, 1, 0, 1/10, negative 1. And it also is going to have an asymptote at x equals 0. Connect my points. So I get really close to this x equals 0 line, but again, I never am actually going to touch it. If you want some more videos on graphing logarithmic functions, you can go to that site. Let's do a couple more graphing of logarithmic function examples that are not just the basic ones. So let's look at graphing f of x equals log base 2 of x minus 1 plus 2 as a series of transformations. We can see with this one, if we match it up with log base a of x, that this matches up with y equals log base 2 of x. So that would be the function that I start with, and then I'll transform that. So if I start with that function and I have it go through a series of transformations, first transformation I would deal with is this minus 1 inside with the x, which means we're going to shift it right 1, which takes your x values and adds 1 to them. And then I'll see that we have this plus 2 on the outside, which means I'm going to shift the graph up 2 units, which means I'm taking my y values and I'm adding 2 to them. So there's a couple different ways you can do this. You can first go ahead and graph this first function and then just take those points and put them through the transformations, or you can do a table and put the table through the transformations and graph that end result. That's what I'm going to end up doing. So when I go to graph these, we learned on that last slide that these all contain the points a, 1. So this a value is 2, so it's 2, 1, 1, 0, and 1 over a, so 1 over 2, negative 1. And then I'll transform those points. Oops, let's make this green. So I add 1 to each x value, so these points become 3, 1, 2, 0, and 1.5, negative 1. And then I'll shift them up 2. So I'll take my y values and add 2. So I get 3, 3, 2, 2, and 1.5, 1. Now the other thing to keep track of is the vertical asymptote. So that vertical asymptote is x equals 0. So when I put that through the transformations, this first transformation says that we add 1 to the x value. So now the asymptote becomes x equals 1. And then this last one, we shift it up 2, so we take the y values and add 2, but since this asymptote is an x value, it's just going to stay the same then. So I have an asymptote at x equals 1, draw that in, and then plot my points, 3, 3, 2, 2, 1.5, 1. Get really close to that vertical asymptote, but never quite touch it. Determine the range and the vertical asymptote. So looking at this graph, you can see that our range is going to be all real numbers. And the vertical asymptote we already said is x equals 1. Find the inverse function. Okay, so remember to find an inverse function, you switch your x and y. So I'm going to set, instead of f of x equals, I'm going to have x equals. And then it's going to be log base 2 of y minus 1 plus 2. So my goal here is to get the y by itself. So to isolate that y, so the first thing that I need to do is I need to get this logarithm part isolated so I can change it into an exponential function. So to get this piece isolated, I'm going to first subtract 2 from both sides. So that leaves me with x minus 2 equals log base 2 of y minus 1. I'm going to go up to here now. So now that I've done that, now I can change this to an exponential. So 2 to the x minus 2 equals y minus 1. And now to get the y by itself, add 1 to both sides. So I get 2 to the x minus 2 plus 1 equals y. And then I'll rewrite this using inverse notation. So the inverse function is 2 to the x minus 2 plus 1. Use f inverse to confirm the range of f found in part C. From the domain of f, find the range of the inverse function. Okay, so use the inverse function to confirm the range of f found in part C. So again, with an inverse function, we can see that this is an exponential function. Since these are inverses, that means that the range of our regular function is the domain of the inverse function. This is exponential. The domain of any exponential is always all real numbers. From the domain of your function, find the range of f inverse. So we can see based on this graph, the domain of this function is x values that are larger than 1. That means that the range of my inverse is going to be x values that are larger than 1. Oops, and these are y's, because we're dealing with y values now. It's the inverse, so all values of y such that y is greater than 1. And now it's wanting us to graph the inverse function on the same axes as f. So to graph this inverse function, you could go through and do a table of values for this graph, or you could just recognize that this is an inverse function. So to graph the inverse, you just switch the x and y values. So looking at this, 3, 3, when I flip those, I also get 3, 3. Actually, I'll do this in blue. 2, 2 is still 2, 2. And then 1/2 1 becomes 1, 1.5. So 1, 1.5 is right here. And this asymptote was x equals 1. So when I switch the x and y there, that becomes y equals 1. So this will have the horizontal asymptote at y equals 1. And there's the inverse function.